Okay, I'm Daniel, and I'm going to be presenting this paper, Defeating Return-Oriented Rootkits with Returnless Kernels. It was presented by this group from NC State at Eurosys 2010. Okay, so OS kernel rootkits, if they succeed, would have unfettered access within the system. So they're obviously very dangerous, and we want to do everything to prevent that from happening. There are already existing techniques to detect and prevent malicious code from being injected into the kernel. However, there's this relatively new as of 2010, concept called return-oriented programming. And these return-oriented rootkits would reuse existing code. So they're not injecting any new code. So those existing techniques would fail to detect or prevent return-oriented rootkits. And so this paper intends to defeat these return-oriented rootkits by completely eliminating the return instruction that these rootkits depend upon. So, before we find out how they defeat these attacks, we need to understand return-oriented programming. And before we do that, there's something a little more basic called buffer overflow attacks that we need to understand. And so if you take a look at this code, if I can pull up my laser pointer. Okay, so this code over here, this is not well-written code. We'll see what's wrong with it in a moment, but let's see what happens when we execute it, when it's executed, the way it's intended to be executed. When this function is called, the return address would be stored on the stack. The stack in this case grows downward. That we're following the Intel convention here. Possibly a frame pointer or some other local variables would be pushed onto the stack. And then this buff variable here that occupies 20 bytes is also stored on the stack, right? So when this function is executed, you have your data that's copied over from the input buffer. And at some point, if your destination buffer is 20 bytes, you expect that the input buffer is 20 bytes or less. And since it's a string, there should be a null. That means there should be a null character within the first 20 bytes. And once this function completes execution, there is a ret instruction at the end. What that does is it'll pop the return address from the stack and jump to this return address. So it'll decrement or increment the stack pointer. By that point, all of these variables have already been popped off the stack, and it'll pop the return address and actually jump to that return address. So yeah, what's wrong with this code? Well, there is no bounds checking, right? So stir copy would continue to keep copying characters until it encounters a null character. So if we don't provide a null character within the first 20 bytes, whatever we pass is just going to keep getting written in beyond the destination buffer, and it'll overwrite the original return address. So now when that happens, when the function tries to return, it'll return to this return address, and we've effectively hijacked the control flow. And originally with these attacks, I think that this was first introduced back in 1996. The first iterations would actually jump to the destination within this buffer itself, and some malicious code in here would be executed. So your payload would actually contain the malicious code. Now, that's no longer possible because we don't allow, we have non-executable stacks, right? So there are ways to circumvent this. I just want to say before that you should, the correct way to write this function would be to replace strcopy by strncopy. And that applies to, I think, any function within the string.h family of functions. If there's an strn variant available, use that. Okay, so we said that this is no longer possible. You can't push your malicious payload into your input. So what do attackers do instead? Well, they push a bunch of random characters, and what they really care about are these addresses that actually overwrite the return address, and they go beyond that. They don't really care about the caller stack frame because we do, there's no intention of returning to the original caller. Initially, the first address that's jumped to is, say, we've called it your gadget 0 address. Gadgets are essentially just small snippets of assembly code. These gadgets could be anywhere within the address space. It could be in the C library, it could be within the kernel. And so you can execute arbitrary code, and the only condition required is that all of these arbitrary code snippets end with a return instruction. So once again, you jump to this first gadget, encounter the red, it'll pop the next address from the stack, and it'll jump to gadget 1. Gadget 1 finishes execution. There's another red, gadget 2, and you can form what's called a ROP chain and execute arbitrary code. And for large code bases like C libraries and OS kernels, it's return-oriented programming has been shown to be Turing complete. So you could literally execute arbitrary code, and there are also ways to automate this process. So we're done with the background. Let's see, the goals of this paper are to create a kernel without any return-oriented gadgets. Now we want to require minimal modifications to the target OS kernel and also minimize performance impact. So we say we want to eliminate all of the return opcodes. So where do those return opcodes come from in the first place? So you have actual return related instructions. This paper focuses on x86 instruction sets. So there are 4 in this case with these opcodes: 0xC3, C2, CB, and CA. x86 is a variable length instruction set. So if you have 2, 3, 4 byte instructions, somewhere within those instructions could be one of the return opcodes, and it's possible to jump to execute code or to jump to positions in the code in such a way that maybe 480F is one instruction and then C3 is a different instruction. You could have immediate operands. So we'll see exactly later on how this translates to something with CB in it, even though you don't see a CB over here. It has to do with relative offsets, and we'll see that later. But assembly code like this could result in return opcodes. And also you have register operands. So in this case, it's the EBX register actually results in another return opcode being introduced. Okay, so this is the first, return indirection is the first method that the authors have come up with, and it targets actual return related instructions. So, again, regular code in assembly, if you call an address, this implicitly means that the return address, that's this address here, would be pushed onto the stack. And once the call function completes execution, return the red instruction, pop that address and jump to it. So what the compiler in this case would do instead is replace this call instruction with a push instruction that, instead of pushing the return address, would push a return index and then jump to the destination address. And this return index is actually an index into a return address table that is constructed offline, and it can be constructed offline because kernel code is mostly static. So we can actually have a table of every possible return address, and we just push return indexes, onto the stack. And then instead of the ret instruction over here, there's a series of 5 instructions. First, we would pop the top of the stack, which in this case would be the return index, right? Store that in some register. This AND instruction here is actually to limit the range. So if some attacker tries to include an index that's greater than this value here, FFFFF, it would get truncated effectively. The next 2 instructions, which are in dark gray, if that's noticeable, what these 2 do is actually compare the type ID of the callee function with the type ID that we've stored in a separate type table, return type table, indexed with the same return indices. And the purpose of that is to make sure that when we return, we are returning to a callee function with, or returning to a function with the same type signature as the original callee. This is just an extra kind of check that they've introduced. And if that check fails, we jump to some sort of error handler. These 2 instructions are optional. And finally, we jump to the address stored in the return address table that's indexed by what the index that we popped into reg A in this case. Register allocation is the second method, and this targets return opcodes contained in register operands. So there are 4 registers that could introduce return opcodes when used as operands. They don't always introduce them. So, for example, in this case, RBX is being used, but this instruction doesn't actually contain any return opcodes. So what we do is in the register allocation phase of compilation, let's say for a particular block of code, we go ahead and allocate the registers, and then we check have any return opcodes been introduced by these instructions. And compilers have a table of available registers. So if we find that return opcodes have indeed been introduced, we just mark those, all of these 4 registers as unavailable and perform the allocation again. And in that case, obviously, we know that there won't be a possibility of such opcodes being introduced, and then we just continue with the rest of the compilation. Peephole optimization is this third method. There are 2 types of peephole optimization. The first one eliminates return opcodes from other instructions. So this is related to the variable instruction length of x86. There's only one instruction that contains a return opcode within its longer opcode. That's move NTI. It's essentially the same semantics as move. The only difference is that it tells the processor that the destination address is unlikely to be used, so that the processor doesn't include that in the cache hierarchy and use up cache memory with rarely used data. So it's just a small performance optimization. What the authors do in this case is simply replace this instruction with a move. And since there are only 8 occurrences throughout the free BSD kernel that they target, the performance impact should be minimal. The second type of peephole optimization, I should probably say peephole optimization is a name given to compiler optimizations in general, and they're called peephole optimization because they just focus on a small snippet of code. Like we saw earlier, one case is relative jump offsets. And so, with this assembly code here, C3 doesn't appear anywhere over here, but this is actually produced by the disassembler, and this address is an absolute address, whereas what's actually encoded in machine code is a relative address. So if you do the math, you'll find that 4F01 plus C3 would give you 4F C9. And so what's done in this case is that this code is replaced by a jump to CA instead of C9, and we just put a no op instruction after this instruction. So we jump one address further. So C3 is effectively replaced by C4 in the machine load. The second case, where immediate operands could contain return opcodes, is just regular use. So, for example, if we have a compare instruction where we're comparing contents of ECX to C3, we can move a different number, C4, into a register, decrement that register, and then compare it with the contents of ECX. Okay, so evaluation, the total of 2100 lines of code was added to LLVM. The authors intended to have minimal modifications to the kernel, and all operating system kernels are going to have some assembly files. So those obviously had to be modified themselves, because you can't use the compiler to change those files. None of the C files were modified. The resulting image size was 9.4% bigger than the original one. And most importantly, all of the 18,330 occurrences of return opcodes were eliminated. As for performance, so they had a total of 4 tasks, 3 of which are shown in this particular graph. And they plotted the performance overhead. And what's more important in these graphs are the first and third columns, because those are the overall overheads. The second and fourth lines indicate overhead within the kernel itself. So that is just kind of benchmark, evaluation of overhead within the kernel. But the more real-world impact would be indicated by lines 1 and 3, and in that case, the worst case is just around 6% for Apache Bench. They also used the LM Bench benchmark, and similarly, it's just under 6% in the worst case for when type-based validation is included. Okay, so to conclude, the authors identified RET instructions as being indispensable for the creation of return-oriented rootkits. And just to rehash the goals that we mentioned earlier, they wanted to create a kernel with 0 return-oriented gadgets, and they successfully eliminated all of the opcodes required to create these gadgets. They wanted minimal modifications to the OS kernel, and they only needed to modify the assembly files and none of the C files. And performance impact is minimal, under 6%, which should be acceptable for most applications, but in reality, there's probably some significant number of people who would not be happy with the 6% performance overhead, and that might be why this hasn't been employed in practice as far as I am aware of. Finally, the last interesting thing I just want to mention is that a few months after this paper was published, there was another paper in CCS that claims to carry out return-oriented programming without returns. So as far as I can tell with my brief reading of that paper, it can defeat the protections introduced by this paper, and that is all part of the paper list of this course. So hopefully someone else will present that as well. All right, thank you. It's done.